Finding inverses is almost never a good idea. That might seem like a perverse thing to say, given the amount of time we've spent on the subject. Let's discuss the issues with finding inverses, then explain why we wanted to talk about them anyway. Speed. The first thing to realize is that finding inverses is a slow algorithm. From a speed point of view, it's the kind of thing that should be avoided. For example, suppose you have a matrix equation AX equals B, where A is large. You decide to solve it using the matrix inverse. You find the inverse, then multiply both sides of the equation by it to get X equals A inverse B. That might seem sensible. You're used to solving non-matrix equations of this form, AX equals B, by multiplying both sides by 1 divided by A. But consider, to find A inverse, we needed to perform Gauss-Jordan elimination on this augmented matrix. Meanwhile, we already had a way of solving the matrix equation AX equals B. In particular, we performed Gauss-Jordan elimination on the augmented matrix AB. The bigger the matrix, the slower the Gauss-Jordan elimination. So if your options are a matrix augmented with a single vector versus a matrix augmented with an entire other matrix, the choice is obvious. Accuracy. What's worse than being slow is that the inverse finding algorithm, both the classroom algorithm we saw and the ones used in practice, are numerically unstable. What this means is that the minor rounding errors that your calculator experiences when it performs floating point arithmetic get worse and worse with every step until the resulting matrix can be quite inaccurate. Between being slow and being inaccurate, matrix inverses are clearly a pretty poor numerical tool. So what does this mean? Did we introduce an entire topic just to later tell you it's all worthless? No, linear algebra lies on the boundary between pure and applied math. You might not want to find inverses as part of a computer program, for example, but their existence is logically equivalent to many interesting things.